There's a place in our solar system where every law of physics seems broken, where an entire planet's heat switch is turned off, where compasses point in insane directions as if the magnetic field is drunk, where you could fall from the tallest cliff in the universe for 12 minutes, enough time to listen to 3 songs, or write your final will. For over 200 years, we thought it was the solar system's weirdest outcast. But the truth? Uranus isn't the exception. It's the rule the universe follows. When we look at the architecture of our solar system, everything seems to follow perfect logic. Rocky planets huddle close to our parent star, Mercury, Venus, Earth, Mars. The asteroid belt divides like an invisible wall. Then comes the kingdom of gas giants, Jupiter and Saturn, spinning majestically like dignified gatekeepers with their brilliant rings. Everything makes sense. Everything has order. But if we dare venture beyond Saturn's orbit, deep into the darkness where sunlight becomes just another bright star in the sky, we'll find something that breaks every rule. This is Uranus, the planet that flipped the world upside down. A pale cyan sphere, silent and deadly cold. For over 200 years since astronomer William Herschel discovered it in 1781, this planet has remained a stranger to us. Uranus is 4 times larger than Earth, but it doesn't spin like a normal top. It rolls around the sun like a bowling ball down a lane. Its axis tilted 97.7 degrees, almost completely sideways. Its surface is incredibly bland. No magnificent great red spot like Jupiter. No glorious rings like Saturn. Just a smooth cyan billiard ball with no remarkable features. But that quiet appearance is a massive lie. Beneath this methane layer lies the strangest environment in our solar system, where magnetic fields twist like a drunken corkscrew, where temperatures are colder than the most distant planet, where moons bear scars of ancient catastrophes. Uranus was the first modern planet, discovered not with the naked eye, but with technology. William Herschel doubled the boundaries of our cosmic backyard in a single night in 1781. But it took nearly 200 more years before NASA decided to send an emissary. In 1977, Voyager 2 left Earth on the rare Grand Tour mission, a journey past all 4 giant planets. 9.5 years. Voyager exploited a rare gravitational alignment to steal speed from Jupiter and Saturn, shot like a bullet into the solar system's depths. On the 24th of January 1986, Voyager 2 flew past Uranus. 5 days. Just 5 days near the planet to photograph, measure, record data. And since then, complete silence. 40 years of silence. Uranus lies 2.9 billion kilometers away. Light takes 2 hours 40 minutes to reach it. A spacecraft needs 12 to 15 years of travel, a large portion of a scientist's career. The mission designer might be retired when the first images arrive, but that long journey will be worth it, because at the end, we'll find mysteries that could rewrite our understanding of the universe. Imagine we're preparing for the return trip. The Uranus Orbiter and Probe mission. Top priority in NASA's planetary science survey for the next decade. Unlike Voyager's 5-day flyby, an orbiter must slow down to be captured by Uranus's gravity. This requires massive fuel reserves and longer travel time. 12 to 15 years instead of Voyager's 9.5. But the reward? Instead of 5 days of observation, we'll have at least 4 years. Enough to witness one complete season on Uranus, where each season lasts 21 Earth years. We'll likely need help from Jupiter and Saturn again, cosmic slingshots to boost speed and conserve fuel. Each flyby steals a bit of kinetic energy from these giants. As we approach, the first thing you notice is the color. Not the brilliant ocean blue of Neptune, but a pale, washed-out cyan, almost ghostly, like looking through a layer of cold fog. Methane in the upper atmosphere absorbs sunlight's red wavelengths, reflecting only blue and green. That's why Uranus looks like a faded cyan pearl floating in darkness. But the most astonishing thing isn't the color. It's the cold. Minus 224 degrees Celsius at the tropopause, the boundary between the troposphere and stratosphere. This is the coldest temperature recorded on any planet in our solar system, colder than Neptune, despite Uranus being 1.6 billion kilometers closer to the Sun. This is the greatest paradox. Jupiter radiates 1.7 times the energy it receives from the Sunday, 1.8 times. Neptune, an impressive 2.6 times. All have internal heat sources from their formation billions of years ago. Primordial heat from collisions, energy from gravitational contraction. But Uranus? Only 1.06 times, nearly zero. For some reason, Uranus's internal heat source seems to have been switched off. The planet's core appears thermally isolated from the upper layers, as if someone turned off the heat switch of an entire world. Or perhaps some catastrophe drained its energy billions of years ago. This is the first mystery, and it might explain everything strange about Uranus. To understand why Uranus is strange, we need to understand how a normal gas or ice giant works. When a planet forms, it accumulates massive energy from millions of collisions. Celestial bodies crash together, melt, and stick. This energy is trapped deep in the core, like a giant furnace inside the planet. Over time, heat gradually moves from the core to the surface, creating powerful convection currents, like boiling water in a pot. These currents drive massive storms, create complex cloud structures, and make the atmosphere dynamic. But Uranus? Its atmosphere is smooth as a polished billiard ball. Very few storms, very few cloud structures, as if someone turned off the engine inside. The question is, why is Uranus so stone cold? The most popular hypothesis: Uranus is the victim of a catastrophic cosmic traffic accident. About 4 billion years ago, during the chaotic early days of our solar system, a massive object, possibly as large as Earth or larger, slammed into Uranus at terrifying velocity. The collision didn't destroy the planet, but was powerful enough to knock it sideways. That's why Uranus rotates on its side at a 97.7 degree tilt. But the consequences may have been far deeper. The impact scrambled the entire internal structure, mixing hot layers with cold ones, creating a thermal barrier between the core and mantle. Imagine a furnace wrapped in 20 layers of wet blankets. Heat can't transfer upward, only trapped deep inside. Uranus might be the wrapped furnace. The energy is still there, but can't escape. The second hypothesis focuses on Uranus's internal ocean itself. Uranus's mantle isn't solid rock. It's an ultra-high pressure liquid ocean. Water, ammonia, methane, and countless dissolved ions, all compressed under millions of times Earth's atmospheric pressure. If this solution has extremely high viscosity, thick as honey or syrup, heat cannot convect efficiently. Try heating a pot of honey. Heat takes forever to rise from bottom to top because the fluid is too thick. Uranus might be a cosmic honeypot, heat trapped in a super viscous ocean, moving so slowly it's nearly stationary. Without internal heat, Uranus's atmosphere should be completely dead, smooth and quiet as a frozen lake. But occasionally, it awakens with inexplicable violent storms. In 2014, the Hubble Space Telescope detected a superstorm on Uranus, with winds reaching 900 kilometers per hour, twice the strongest storm ever recorded on Earth. Where does the energy come from? Nobody knows. Uranus is like a critically ill patient lying quietly in bed, but sometimes jolting awake with violent convulsions, then sinking back into deep sleep. To solve this mystery, we need to return. Not fly past in 5 days like Voyager, but stay at least 4 years with precise instruments, like a CT scan for a planet, to reveal the true internal structure. But temperature isn't the only mystery. Something even crazier hides beneath that pale cyan surface. On Earth, the magnetic field is an invisible shield protecting us from solar wind, a stream of charged particles blasting from our star at millions of kilometers per hour. Earth's magnetic field is generated by a spinning liquid iron core, a giant natural dynamo. The magnetic pole tilts about 11 degrees from the geographic pole, nearly perfect. Compasses work reliably. Auroras appear exactly where they should, at the north and south poles. Now, forget all that, because Uranus plays by completely different rules. When Voyager 2 measured Uranus's magnetic field in 1986, scientists thought the instruments were broken. The number was too crazy. The magnetic pole tilted 60 degrees from the rotation axis. For comparison, imagine if Earth had Uranus's magnetic field. The magnetic North Pole would be in Brazil. If you stood at the North Pole with a compass, the needle would point straight down towards South America. Migrating birds would be completely lost. GPS systems would collapse. On Uranus, the rotation axis and magnetic axis don't align at all. A geometric chaos of horrific proportions. But it gets stranger. The center of the magnetic field isn't located at the planet's center. It's offset about 8,000 kilometers, equivalent to 1/3 of Uranus's radius, toward the southern rotational pole, like holding a bar magnet. But the magnetic force emanates from near one end instead of the middle. This creates a terribly asymmetric magnetic field. One hemisphere has a strong magnetic field. The other is weak. Solar wind attacks unevenly, like an umbrella with holes on one side, perfect on the other. One half of the planet is well protected. The other half, directly exposed to cosmic radiation. Uranus doesn't create its magnetic field like Earth. It doesn't come from a metallic iron core. Instead, the magnetic field originates from a conducting ocean in the mantle layer. Water, ammonia, and countless dissolved ions, all swirling under extreme pressure and temperature. Imagine a giant battery filled with salt water being violently shaken continuously. That's how Uranus creates its magnetic field. Earth generates magnetism from its heart, molten iron core. Uranus generates magnetism from its guts, liquid mantle layer. That's why it's so skewed and unstable. Now, combine everything. Planet tilted 97.7 degrees. Magnetic field tilted another 60 degrees. Magnetic center offset 1/3 of the radius. Result? Uranus's magnetosphere opens and closes to solar wind every 17 hours, 14 minutes. The length of 1 day on Uranus. Morning. Magnetosphere shields solar wind well. Noon. Half the hemisphere is exposed. Evening. The entire planet is unprotected. Midnight. Cycle repeats. Like a corkscrew getting more tangled with every turn. Consequence. Auroras on Uranus don't appear at the poles. They can appear anywhere. Near the equator, at mid-latitudes, even directly overhead if you stood on the planet's surface. A planet with an unpredictable magnetic field. And it might help us understand thousands of other planets out there experiencing the same thing. Uranus isn't alone. It's surrounded by 27 known moons. And one of them is the strangest world ever discovered. This is Miranda, a tiny moon just 471 kilometers in diameter, 7 times smaller than our moon. But its surface looks like it was torn apart and reassembled by a giant child who didn't know how to do puzzles. Scientists believe Miranda was once shattered by collisions into multiple pieces, but gravity pulled the fragments back together in the wrong places, a Frankenstein world of the cosmos. And lying on this chaotic surface is the tallest cliff in the solar system, Verona Rupes, a nearly vertical ice cliff 20 kilometers high, twice the height of Mount Everest. For comparison, the deepest part of the Grand Canyon is only 1.6 kilometers. Olympus Mons on Mars is 21 kilometers tall. But it's a gently sloping mountain, not a vertical cliff. Verona Rupes stretches for hundreds of kilometers, cutting across Miranda's surface like a giant scar from an ancient catastrophe. But here's what's truly miraculous. Gravity on Miranda is only 0.8% of Earth's, nearly non-existent. If you fell from the top of Verona Rupes, it would take you 12 minutes to reach the bottom. 12 minutes. On Earth, falling the same 20-kilometer distance takes only 64 seconds, and you'd hit the ground at twice the speed of sound. Instant death. But on Miranda, gravity is so weak, you fall like a feather. Imagine this. You're standing at the edge of Verona Rupes, looking down into bottomless darkness. Above, Uranus occupies 1/3 of the sky, a ghostly cyan sphere, silently watching. You gently push yourself off. You don't fall in the normal sense. You float, drifting downward. The first second, velocity increases extremely slowly. After 1 minute, you only reach 17 kilometers per hour. Jogging speed. You can still see every crack in the ice wall clearly. Sunlight, dim as candlelight, reflects off the ice, sparkling like crystal. Complete silence. No wind sound because there's no atmosphere. Only your heartbeat in your helmet speakers. 4th minute. Velocity around 100 kilometers per hour. The ice wall slides past faster, but still very slow compared to falling on Earth. You have time to think, recall your life, or simply enjoy the view. The ice wall reveals many colors. Pale blue, pure water ice, yellowish brown, ice mixed with ammonia, black, carbon, and ancient organic matter. In 12 minutes, you fall down an abyss deeper than Mount Everest, but have enough time to write your final journal entry. 11th minute, final velocity 200 kilometers per hour. The bottom appears, ice hard as rock. You hit the ground with force equivalent to jumping from a 6th floor building on Earth. Painful? Certainly. But with modern spacesuits equipped with shock absorption systems, you could survive 12 minutes. Enough to listen to 3 songs, watch half a short episode, or face eternity. On Earth, death from great heights comes quickly. No time for reflection. But on Miranda, death gives you 12 minutes to think about everything. Is that a curse or a gift? Verona Rupes isn't just the tallest cliff in the solar system. It's where time slows down, where you can face your fate slowly. And when you stand up from the bottom, if you survive, you'll look up to see 20 kilometers of blue-white ice stretching into the sky. And you'll realize the universe is full of places where the laws of physics create unbelievable moments. For most of human history, we only knew 8 planets, and we believed our solar system was the standard, the template the universe used to create planetary systems. Small rocky planets close to the star, giant gas planets far from the star. A logical, predictable order. But then, in the late 20th century, we started looking outward, and the universe shocked us. Since 1992, we've discovered over 5,500 planets orbiting other stars, and they're nothing like what we expected. Hot Jupiters, giant planets just millions of kilometers from their stars. 1 year lasting 3 Earth days. Super Earths, rocky planets, 2-3 times larger than Earth. But our solar system doesn't have this type. And then the most common type, The most common planet type in the galaxy isn't rocky planets, not gas giants, but sub-Neptunes, planets the size of Uranus, or smaller Neptunes. According to data from the Kepler Space Telescope, approximately 35 to 40% of all exoplanets are sub-Neptunes. This is the most common planet type in the known universe, and we only have 2 in our solar system. Uranus isn't the outcast. Uranus is the prototype. Imagine this. You grew up in a family of 7 people, 4 short siblings, 2 giants, and you medium height. You think, my family is normal. But one day you go outside and discover 90% of other families have all medium height people like you. Suddenly, you realize you're the standard. Your family is the weird one. Why are there giants like Jupiter? Why are there short people like Mercury? That's exactly Uranus. We've had it backward for 200 years. The solar system isn't the standard. It's a rare exception. If we don't understand Uranus, the representative of the most common planet type in the universe, how can we find life beyond Earth? How many sub-Neptunes out there have subsurface oceans? What's the real internal structure? Is the crazy magnetic field standard or exception? Are there any environments for life? Uranus holds the key to understanding billions of planets out there. We're not flying to Uranus to discover the strange. We're flying to understand what's normal in the universe and perhaps find the answer to the biggest question. Are we alone? Because if life can exist on a cold, crazy, flipped over world like Uranus, then life could be anywhere. The scientific community has decided. In NASA's decadal survey, the Uranus Orbiter and Probe mission ranks as the highest priority in planetary exploration. If approved, the spacecraft will launch in the early 2030s, possibly as early as 2031. The journey will last 12 to 15 years through the cold darkness of the outer solar system. Arriving in the 2040s, the orbiter will study Uranus for at least 4 years, one complete season on this planet, where each season lasts 21 Earth years. The probe will plunge into the atmosphere, measuring chemical composition, temperature, and pressure at each layer. Finally answering questions, does it really rain diamonds? What's in the internal ocean? Why is heat trapped? Uranus, the planet with its heat switch turned off, with a magnetic field as crazy as a twisted corkscrew, with a moon featuring a cliff that gives you 12 minutes to contemplate life. Not an outcast, but the standard blueprint the universe uses to create billions of planets. We're not flying to Uranus to discover the strange. We're flying to understand what's normal in the universe, and perhaps find the answer to the biggest question. Are we alone? Because if life can exist on a cold, crazy, flipped over world like Uranus, then life could be anywhere. Uranus awaits us, spinning in cold darkness, 2.9 billion kilometers from the Sunday, holding secrets of its violent history, holding clues about billions of other worlds. It's time we return, not to conquer, but to listen, to understand, to find our place in the much larger story of the universe. The planet that flipped the world upside down is waiting to flip our understanding once again.